Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use free body diagrams and Newton's laws of motion to analyze systems. So in this example, imagine we got this poor dude here. He's pushing on that large yellow box with a force of 200 newtons. So I drew a force vector 200 newtons to the right. Here is what he's applying. This 30 kilogram box is sitting next to a 20 kilogram box. And what we're going to do is we're going to try to find the acceleration of the system and the force applied on the 20 kilogram box at the surface. In this example, we're going to assume friction is small or negligible. I'll go ahead and work another video to take a look at what demonstrate how to incorporate friction into it. But for this video, I'm just going to keep it as is. All right. So the important part of these problems is knowing how to draw the free bodies and what to draw the free bodies of. And there's three different possible free bodies really I could draw for this system. Possibility number one, I might draw a free body of this. Now, that's perfectly fine. Let's talk about what that free body would look like. It would have a 200 Newton force to the right. It would also have some sort of force between these, which would be to the left on the 30 Newton or the 30 kilogram box. Now, that force would be unknown, and we also do not yet know the acceleration. So that equation, if we do that, it's going to have two unknowns. So I'm going to back up here and talk about, well, what else can I do? Another possibility is we could draw a free body of this. Now, if we draw a free body of that animal, all right, we're going to have an unknown force here acting right on this surface, and that force is going to be to the right. We also have an unknown acceleration, so that any equations we write from that free body also going to have two unknowns. Third option is a free body of the entire system. If we draw a free body of our entire system, there's a very important thing that must be realized. The force interaction here at this surface is an example of what's called an internal force. It doesn't affect the acceleration of the system. That force is to the right on the 20 kilogram mass, but it's to the left on the 30 kilogram mass. And even if I try to include it, it's going to add to zero anyway. So I would recommend starting with a free body of the entire system. Now, when we draw free bodies, let's see if I can lasso that system here. Whoops. Got another green line to get rid of. All right. When you draw a free body, give me just a moment here to do. Oh, yeah. All right. You don't want to draw your free body here. It just muddles up the picture. This is just a picture that's describing the problem for me. When you draw a free body, what you want to do is you want to redraw the system. Easier for me to do that than you. So I'm going to copy that, and then, oops, what happened here? Darn it, I'm going to have to try that again. There we go. And now we're going to copy, paste. So what you want to do is do that with pen and paper. Just redraw the system. Now what I'm going to do is I'm going to draw force vectors acting on the system. So this 200 Newton force here, I'm going to start with that. That's applied right here on the system to the right. So I'm going to put a force vector there. I can label F or 200 newtons. I'll go ahead and just label it 200. All right. Now, this system here has a certain weight, a gravitational force acting on it. We've got a choice here. We could put a pair of gravitational forces, one where the mass is 30, 120, or we can just put one gravitational force. I'm going to go ahead and choose to do that. I'm going to put one gravitational force down, label it mg. I'm just going to take note that that mass would be both of them. Right? Surface and contact. This system is being supported by the ground. That's going to create what we call normal force. That normal force would be up. And that's pretty well it. If we wanted to include friction, it would be included at this bottom surface here, and it would be to the left. But again, for this example, I'm going to assume friction is small, and I'll go ahead and show how to incorporate that into other problems. All right. So that's it. I don't see any other forces. And again, here's how you tell. what I usually do is imagine this boundary around the system that you're analyzing, and you're looking for things coming from outside that boundary. See this guy's hands coming from outside that boundary. The ground here is coming from outside that boundary. But that's it. There's no other entities coming from outside that boundary. So we've got the gravitational force and the applied force of 200 newtons and the normal. And that's it. So next step, we write our Newton's second law equations. So Newton's second law is net force equals ma. Remember, it's a vector law. And what that means is, by net force, we mean the sum of all forces. So we apply it by direction. I'm just going to take note that the normal and the mg, probably by observation, you know that they're going to be equal in weight. They're going to sum to 0. The net force is this one to the right. So I'm going to go ahead and write out this equation here. Sum of all forces in the x direction equals ma. And again, I'm calling right the positive x direction. So that equation is going to be 200 newtons equals m, which in this case is 50 kilograms, times a, the acceleration of the system. It's pretty easily solved for a. We get 200 newtons over 50 kilograms. That's 4 newton per kilogram. Now remember, a newton is a kilogram meter over second squared. So that works out to 4 meter per second squared. So this acceleration means that this system, right, is going to accelerate to the right at about 4 meter per second squared, or 4 meter per second per second. All right, we got one of these down. Boom, we know the acceleration of the system. All right, now, net force on the 20 kilogram mass. There's two choices here. We could go back and draw a free body of this. Now we talk about what that free body would look like. This 200 Newton force would be acting on that free body. It's a force to the right. We would have an mg down for the weight of this object, a normal force because of that surface and contact. Then we'd have another normal force in between these, and that normal would act to the left on the 30 kilogram object. We could solve that free body for that normal, no problem. We also could draw a free body of this part of the system. And I'm going to go ahead and do that because it's just going to be the simpler part, the slightly simpler free body. It's going to have a gravitational force down. We've got a normal right there, and we have a normal here between these two surfaces. So that's the one I'm going to draw. That one's only going to have one unknown. It's going to yield a nice easy equation to find that normal. Again, the first free body would have been just about as nice and easy. So when you draw a free body here, make sure that you redraw the system that you're looking at. So I am going to copy that. Right? So what you would do on your paper is you would draw that system, whatever part of the system you're drawing a free body of. Right? Now I'm going to start putting force vectors on it. Now there's two different normals here. Right? There's one at this surface, one at this surface. I'm going to go back and give these objects names here because it'll help me with the with this free body. I'm going to call this object 1. Whoops! I'm going to go back and do that in black. Right, so I'm going to call this object 1 and this object 2. Right. Now, the normal force between these is to the right on object 2. And because it's the normal between 1 and 2, I may actually use that to name it. I might call it something like N12, normal between 1 and 2. Right. Another surface in contact right here. That's going to give us another normal. That normal is going to be up. That's the normal between object 2 and the ground. So I might put N2G on there. Again, it's not the same as this normal, so we can't give it the same name. We also have a gravitational force down, mg. And that's it. Those are the only forces acting on the 20 kilogram mass. Again, if there was friction in this problem, we would include it, but there's not. So. And I'm going to take note this object's accelerating to the right, so when we apply Newton's second law, sum of all forces equals ma, right positive. That's just going to be normal 1, 2. Now looking at this free body, This thing does not have an x component. This does not have an x component. This does. And N12 is the complete x component. So that's going to equal m, 20 kilograms, times the a, the acceleration, which we know to be 4 meters per second squared already. So the normal between 1 and 2 is going to come out to be 80 kilogram meter over second squared. And a kilogram meter over second squared is a newton, so that's going to equal 80 newtons. There's the normal between them, folks. So I hope that this problem demonstrates how to draw different free bodies and apply Newton's second law. Again, really important fundamental here is understanding the different free bodies and how to draw them. And again, I want to go back and kind of review that. If this is how we define our system, it's very important to realize that normal does not show up in that free body because it's an example of an internal force. Even if I did put it there to the right, I've got another one acting to the left on the 30 kilogram mass. That's Newton's third law. Remember, forces always appear in pairs, equal magnitude, opposite direction. So it's very important to realize that free body of this system does not include that normal. And that allowed me to find the acceleration right away with one nice easy equation. Right? Then we kind of dig into the system. Free body of this does include the normal, and we already know the acceleration, so it became a pretty easy problem to find that normal. And again, it would have been almost just as easy to do a free body of this. And as an exercise to the reader here, I would suggest you draw that free body. It should have 4 forces. Some forces in the x direction equals ma, and you should get 80 newtons out for the normal between these forces. So I'm going to go ahead and leave that as an exercise to anybody watching this video. I hope this helped demonstrate these concepts. Have a great day.